There are three ways in Algebra 1 that we learn to solve systems of equations. And the first we're going to learn is solving systems by graphing. Now, I already kind of showed you this in the introduction to solving systems of equations, but I'm going to show you some more graphing techniques and what happens when some of the graphs look the way they do. So for this, you're going to need this handout here. Okay, it says types of solutions. You're going to cut out this large rectangle, this large rectangle, okay, and then this large rectangle, and they're going to be stacked on top of each other. So I'll show you what that looks like in a second. Why don't you pause and then you can cut. So let's start with these two larger rectangles here. Okay, so you should have cut this one out, kept this top part, and then this one out as well, and kept the top part. Now let me show you the different types of solutions you'll have when encountering systems of equations. The first one is the most often one you'll see is when a system has one solution. Okay? And that occurs when the lines have different slopes. You're going to write the word different there. Okay? And when there is one point. Of intersection. So you see in this system of equations at the top, we have y equals 3 over 2x plus 1, and y equals negative 1/2 x minus 3. Now both of those equations have different slopes. Okay. They're going to cross, you see how they're graphed here, at one point, and that point is the solution. Now, there's going to be occasions when there are no solutions to a system, just like we have no solutions to some regular equations. Okay? And no solutions occurs when lines have the same slope. Okay? In other words, you learn that lines that have the same slope are called parallel. Now, parallel lines, by definition, never touch. So those lines right here that both have a slope of -1 are never going to cross. They're parallel, so they won't have any point that's in common. So there is no point of intersection. Finally, infinite solutions. Now, infinite solutions occur when you've graphed a line on top of another line. For example, y equals 2x plus 2 and 4 equals 4x plus 2y. Well, these are really the same line. So when they're graphed, okay, they're going to be graphed right on top of each other. So lines that have the same slope okay, and I want you to put like a star here and y-intercept. Okay, well, those have infinite points. Of intersection. Now you're going to put this in your book, and how you do that is you're going to take this bottom one and you're going to put some glue on the tab. If you don't have glue, you can just tape it down up here, but don't tape the sides. And you're going to take this piece here and you're going to place it right on top of the glue. It's kind of like a gluing tab. And then we have this right here. It'll flip up Okay. And we actually want them to flip up individually, so we're just going to cut along this edge here. Right up to the gluing tab. And now these should flip up individually. Don't mind the glue that just fell on the ground. Now, what you haven't worked with yet are these three bottom equations here. Okay. Your task is to cut these apart. Okay. And once they're cut apart, you're going to place them underneath wherever they follow. So if this one here is a one solution equation, you would put it under here. And you'd glue that down. And we're going to glue the top tab down. Okay, and then they'll flip up and you'll have an example. So you'll be able to see a finished product pretty soon, because what I'm going to do is I'm going to pause the video and give you a chance to solve each of these systems. Okay. So you should pause the video too, work on these three systems, and I am going to pause the video. And so for this one we have y equals negative x plus 1 and y equals negative 1/2 x plus 2. So I chose this one to do first because they're both in slope-intercept form. There's not a whole lot of work involved. So I'm going to use two different colors. Blue is for my first equation, red is for my second one. Now let's graph this first equation. It's in slope-intercept form, so 1 is going to be my y-intercept. So it occurs there. My slope, though it doesn't have a number, is negative 1. So that's down 1 to the right 1, down 1 to the right 1. Keep going. Or up 1 to the left, up 1 to the left. Because really it's down 1 to the right again anyway. And you can draw in those lines. Okay? That's my first equation. Now, for the second equation, again, it's in slope-intercept form. It's nice and neat. I'm going to start at my y-intercept, which is 2. My slope is negative 1/2. So negative 1/2 is down 1 over 2. Down 1 over 2. Or up 1, left 2. Up 1 to left 2. And you'll see, even by just making those dots, we can see that they're going to intersect at one point right there. So I can draw in that line. And so this one is going to have one solution. Okay. And that solution is -1, -2, okay. And then 1, 2, 3. So -2, 3. It'll be better to put it right there. And so our next system, they're not both in slope-intercept form, but the first one is, so we can start off by graphing that one. We have y equals 2x minus 3. So the y-intercept on this one's -3. That's -1, 2, -3 here. And the slope is 2, which is up 2 over 1, up 2 over 1, up 2 over 1. Right. And now I'm going to use my kind of makeshift straight edge. I'm sorry, the camera's blinking again. see if that's any better. So we've got y equals 2x minus 3, and that's the equation, or the line of that equation. And now let's graph the second one. Sorry. For this one, this second equation here, we are going to put this into slope-intercept form. So let's add 2y to both sides. Okay. Subtract 6 from both sides. Divide everything by 2. And what did we just notice? Right? 2x minus 3, 2x minus 3. They're the same equation. And when I graph this one, I would start at negative 3, up to over 1, up to over 1, up to over 1. Again, there's my line. Red and blue. I think that makes purple. Kind of. But you'll notice that, well, where do they intersect? An infinite amount of points. They intersect at every single point on this line. So this one here is going to be infinite solutions. Okay, I can put that right up here. Infinite solutions. Now for my last system, I've got y equals 1/3 x as my first equation. So this one, well, it doesn't look like there's a y-intercept. The y-intercept is actually 0. I could put a plus 0 here, and it would be in slope-intercept form. It's obviously already in slope-intercept form because you don't have to write the plus 0. But we're going to start at 0 and use our slope of up 1 over 3, or down 1 over 3. And I'm going to use my makeshift straight edge here to draw the equation, or the line of that equation. And now I've got my second equation, which I'll do in red. So 9 equals 3x minus 9y. Okay. Now, one way to use standard form is we can put this in slope-intercept form and graph in using that method. But there's a faster way called the cover-up method, and this one works nice for that. So the cover-up method means if I want to find the x-intercept, I'm going to cover up the term with y. And I have 9 equals 3x. Well, if 9 equals 3x, if I divide 3 on both sides, then x equals 3. So my x-intercept is going to be at 1, 2, 3. Okay. Conversely, if I cover up the term with x, I get 9 equals negative 9y. Divide both sides by negative 9, and I get y equals negative 1. So my y-intercept is at negative 1. And look at that slope. Up 1 over 3. Up 1 over 3. So when I graph this, they have the same slope. So these lines are going to be parallel. Okay. They're never going to touch. And parallel lines, if they're in a system, have no solution. So this system has no solution. So you might be wondering how you're going to end up putting this in your book. Here's what we did previously, the types of solutions. We had a sheet under this, and we put a piece of glue on top of that sheet. And this kind of folded up, and that's what happens for one solution. This flips up too. Okay. So how we're going to make this work in our book is we're again going to take a piece of a stick of glue, and we're going to glue just the tab part here. And we're going to glue that down so it fits in our book. Right like that. Okay, now we graphed 3 different systems. Okay. And so our task is, well, we want to know which category these systems fell in. One solution is here. So I'm going to take this graph as one solution, and I'm going to glue the whole thing down right there. Put some glue in the back. X marks the spot. And just glue it down. So now I have an example, and when I flip it up, there's my example. And do the same for these other 2. So now our finished product, it should look like this. Those are the types of. On the left side, I'd like you to do the following practice problems. You're going to solve the following systems by graphing. The first one is y equals negative 5/3 x plus 3, and y equals 1/3 x minus 3. Number 2 is 4x minus y equals negative 3, and x plus y equals negative 2. And the bottom one is y plus 2x equals 2, and negative 6x minus 3y equals 6. And I'll just zoom in here to those. Make sure you can see them okay. And when you've got these 3 systems graphed and you have their solutions, please go show your teacher.
In this problem, you will write a system of equations. Scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below. After how many months did the alligators weigh the same amount? Alligator 1 initially weighs 4 pounds and grows at a rate of 1 5/10 pounds per month. Alligator 2 initially weighs 6 pounds and grows at a rate of 1 pound per month. Relate the terms to each other in order to build an equation. The weight of an alligator is the initial weight plus the growth rate times the amount of time it has been growing. Now, define your variables. Let W equal the alligator weight. Let T equal the time in months. Now write the equations. First, write an equation that represents the weight of alligator 1. The alligator weight can be represented as W. Is means equals. The initial weight of alligator 1 is 4 pounds, plus the growth rate of alligator 1 is 1 5/10 pounds per month, times time is represented by T. Now write the equation for the second alligator. The alligator weight can be represented as W. Is means equals. The initial weight of alligator 2 is 6 pounds, plus the growth rate of alligator 2 is 1 pound per month, times time is represented by T. The first alligator's equation is W equals 4 plus 1 5/10 times t. The second alligator's equation is W equals 6 plus t. Graph both equations in the same coordinate plane to see when their weight is the same. For equation 1, the slope is 1 5/10, or 3 divided by 2, and the w-intercept is 4. For equation 2, the slope is 1 and the w-intercept is 6. Start at the w-intercept 4. Then use the slope to find the next point by going up 3 over 2. Then draw a line through the points. Start at the w-intercept 6. Then use the slope to find the next point by going up 1 over 1. Then draw a line through the points. Find the point of intersection. The lines intersect at the point 4, 10. This means that after 4 months, both alligators weighed 10 pounds. Is there another way to solve this problem? Yes, you can make a table. Show the weight of each alligator after 1 month, 2 months, and so on.